Hi, everybody. I think I get the easy job today, maybe, and just to give you an overview of DEF and where we see it in the ACI codes and how it affects our internal temperature limit in our mass concrete code in ACI. Okay? If you disagree with me on anything, you can throw tomatoes at me anytime or just raise your hand. Okay, so I'm sure most of you have seen the publication Ettringite, the Sometimes Host of Destruction, which is kind of really funny to me. It's hilarious. Like, well, is it sometimes? Sometimes not. But I think there's some genius in it because ettringite is both really good and it's omnipresent in concrete with Portland cement, and it also can things can go wrong, and ettringite can be very, very destructive to concrete. So just as a very high-level primer, ettringite is also known as calcium sulfoaluminate, and in the jumbled chemistry speak of concrete, it's probably not your typical chemical equation, but it's chemical sulfoaluminate, so just know it sulfates and aluminates in concrete. We have to have calcium sulfoaluminate because we have to have gypsum added to our calcined Portland cement so we don't get flash setting. And it kind of slows things down a little bit so we can finish our concrete. The gypsum in the Portland cement reacts with calcium aluminate in the cement, and it produces a very stable form of ettringite. So what I wanted to do is show you okay. I really like looking at ettringite in blown up view because it really just looks like a bunch of needles and they orient different ways. It's kind of very distinguishable, so you know when you have ettringite. And actually, a lot of times when you look at concrete, if you've taken a concrete sample from the field and you look at it under a microscope, you'll typically, and if there's any water anywhere near it, you'll see some ettringite in the air voids, or sometimes even in the cracks if there's water anywhere near it. And this stuff is okay. It's there. It doesn't really hurt or help the concrete. This is an example of a job where there's a lot of ettringite just hanging out on the surface. It tends to dissolve, and then it comes out on the surface. I have a lot of it in my basement. I vacuum it up about once a year. Otherwise, it just starts to flake all over my laundry. Probably because there's a ton of water behind the wall in my basement, but so far, I haven't seen the water coming through the wall, so I think we're okay. This is okay too. It looks bad, but for the most part, it's okay. This concrete is stable. There's not a lot of steel in it. Steel isn't corroding. So it looks like it's going to fall over because there's all this weight on it. Not a big deal. Now, I was going to write bad ettringite, and I've been corrected so many times in the last 6 months that we don't have bad things, we have challenging things. So I'm just going to call this challenging ettringite, okay? So, the exact mechanism, and smart people in the room may disagree with me on this, but I don't think we 100% understand totally what the mechanism is that causes ettringite to become, I'm just going to say the bad ettringite, okay? And high level, what happens is, it goes into solution when the concrete is curing, and it kind of hides itself. And your structure can be around for like 5, 10, 15, 20 years, whatever. And under the right temperature and under the right moisture conditions, that ettringite is not stable, so it comes out of solution and it starts growing. And there's like a freight train without any brakes. There's no stopping it. So these crystals form, and they kind of explode the concrete from the inside out. Some of the indications in concrete from the cement that will give you an indication that there might be a possibility for DEF is the molar ratio of the sulfate to illuminate, because there's some control happening there, your initial curing temperature, and then just these bullet points don't necessarily go in grammatical order here, but it likes to form in the ITZ, right, in that interface between the concrete and the aggregates, and that's something that I learned. So this is one of those gobbledygook plots that you're just probably all staring at, you're not really reading. I understand that. But what I want to point out, so this is the storage period. Somebody made concrete, and they exposed it to higher temperatures during curing, and this is the expansion. So you have 100 degrees Celsius, which for all of us U.S. people is 212 Fahrenheit, so that's boiling. 90 degrees Celsius, 85, 80, 75. So you can see that as the curing temperature, and not for long, right? 11, 12, 13, 15, 16 hours, increases, the expansion in the concrete or the mortar samples increases. And just keep that in the back of your head. But I'm not really here to talk about all the nooks and crannies of DEF. Really, I'm here to show you how we look at it and how it's impacted our specifications at ACI. So when I started doing mass concrete, I was so confused. I was looking in 207, which is the mass concrete document. Where does it say I need to limit my internal temperature to 160 degrees? Well, it certainly is nowhere to be found in 207. It's in 301, which is specifications for concrete construction. Now I know that for certain. But it's kind of funny, you have to remember it, right? So in section 8 of 301, there is a mass concrete section, and among other things, it says that the maximum temperature of concrete after placement shall not exceed 160 degrees Fahrenheit. Now this just changed. For many years it was 158 degrees Fahrenheit, because if you convert 70 degrees Celsius to Fahrenheit, it equals 158. But luckily we just kind of round it up. Most people do, some specifications don't. We're not making pianos, 2 degrees doesn't matter. So we're good, okay? So where did this number come from? Now, as far as I can tell, I know that the Bureau of Rec has been working on dams from, before we had cars. But I'm not going to worry about the Bureau of Rec. All the documentation that I looked at pointed to this document from Heinz and Ludwig, published in 1987 in a special ACI publication. And that 160 degree internal temperature limit is based off of this publication. What these guys did is they were found out, or somebody told them, or they, were privy to information that precast heat-treated members that had been exposed to moisture were showing excessive cracking. So they're like, I wonder what's going on here. And they made a bunch of mortar prisms. They stored them for 2 hours at 70 degrees, followed by 12 hours storing at from 60 degrees Celsius, which is 140 degrees Fahrenheit, to 100 degrees Celsius, which is 212 Fahrenheit. They also kind of looked at the sulfate to illuminate ratio, and they looked at curing after the 12 hours at an elevated temperature. They put the samples back in a 70-degree room, and they looked at the effect of different humidity levels on the expansion in those samples. Okay? So, very, very high level. This is the same plot as you saw before. But here we have a little bit of expansion in some of those samples at 75 degrees Celsius and a lot more at 80 degrees Celsius. So I think they just rounded down, and we were stuck with 70 degrees Celsius because there was no expansion in their mortar samples below 75 degrees Celsius. They didn't even show 60 on here. We'll just say there was no expansion. And kind of from everything that I've been reading, that's essentially others' experiences, okay? So this is why we have this limit. Now I wanted to show, so concrete is really boring when it behaves, right? It's way more fun when it fails or when there's some sort of distress. I mean, it's not for the owner, right? But definitely not for the contractor, but definitely for the likes of me and a lot of you in this room. And so this is from a publication, a Ryland publication, in 2002. There was some various structures across Europe that were showing this kind of distress. And it kind of looks a little bit like ASR stress, but I think the consensus was that it was some ASR and some DEF, but mostly DEF. And this is just kind of what structures look like. They realized that most of these structures were, when they were poured, got over 80 degrees Celsius. So that's 176 Fahrenheit. Okay. So, we were all great with 158, 160 degrees. Then 201 came along and threw us for a loop. Okay? I mean, I actually really like this provision. And this is a photo that I had to take of my computer screen because I did not have the original document, and there was absolutely no way I could take a screenshot of the ACI document. I know we've all encountered that. And I was doing it too last minute to actually ask Chris. So, this is I think it was 2016 because that was the first 201 document that I could find this particular chart. They're giving us a little bit of a way out in the mass concrete world for the maximum internal temperature. And for those of you who can't read what is on the screen, because I can hardly do it from where I'm standing here, what this does is it allows an increase of the maximum internal temperature from 160 to 185 degrees Fahrenheit in concrete. We'll say mass concrete, but really it's any concrete. If a certain percentage of the Portland cement is replaced with either slag or fly ash or metakaolin and a little bit of silica fume, but we're really not sure about silica fume. But we're going to throw it in there anyway. That must have been a huge discussion. Glad I wasn't there. So this, and I'm not going to read this to you, but it's table 6.2.2.2 in 201, and it's in 16 and then also in the new one, that 23, I think, that this is what I pulled this from. So part of my job was to say, well, where do these numbers come from? Whoa, where did these numbers come from? So as you can see on the bottom, there's these 4 papers. And I was successful in finding 2 of them, not all 4 of them. But they all kind of cross-reference each other and the same other ones, so we're good. I think we got ourselves covered. And really quickly, and if I pronounce this wrong, is Ramlaken? Huh? Okay, you guys are mumbling, but this guy. 2003, so there had been some observations just in general that if the concrete had a substitution of any portion of the Portland cement with fly ash or slag, there typically wasn't DEF. And there were some really, really good examples where, like, the contractor had started off using 100% Portland cement concrete, and then halfway through they realized that the concrete was getting really hot, so they switched in some fly ash. And then 10 years later, you have this really good example of mass concrete that is experiencing DEF, and same mass concrete with a little bit of fly ash that's not experiencing DEF. So, like, hey, we're onto something here, right? So I'm kind of running out of time, but I just want to say that this gentleman's work, along with others, showed that the percentage replacement of metakaolin, slag, and fly ashes, and he considered different kinds of fly ashes, low alkali, low sulfate, high sulfate, moderately high alkali content, and high alkali content fly ashes, class C, and then some class F fly ashes that had low alkali and sulfate. So he looked at a lot of different substitutions, and found that you want to put at least 8% metakaolin. Let's just, again, silica fume, not really that effective, but we'll let it sneak in there. slag at least 25% replacement, and fly ash between 25 and 35% replacement, you can increase your internal curing temperature limit to 185. So just again, really quickly, Thomas put out this paper in 2008, although it's based on an occurrence of bridge piers that were built in 1980 that by 1990 had experienced severe DEF. And he had taken cores out of the bridge piers, and then he had tried to recreate the concrete from the bridge piers in the lab and expose them to high temperatures and high sulfate curing environment, and then just lime water. So this is the situation where I think they had built some of the bridge, and then they realized it was getting really hot, so they put in the fly ash. So it, unbeknownst to the contractor and everybody involved, it was a really great research project. And really quick, this is an example of an aggregate. For those of you who don't look at petrography, this is an aggregate, and these are the DEF needles all around the piece of aggregate, and in this crack. And as you can see, this is just a pure DEF experience. There's no ASR because the aggregate looks pretty good, and there's no gel rim around here. He looked, of the 4 bridge piers, one of them, DEF, was the only cause of distress. In B and D, it doesn't make any difference. In 2 of them, there was both ASR and DEF observed, and then in one of them, there had been fly ash added to the mixture, and so there was no distress. And this picture on your left shows fly ash particles, these spherical particles, and there's no distress, relatively. And this is from one of those columns where you have an ASR situation going on, and you have ettringite around the aggregate particle. So that's what's going on inside.